All right, so if we were to now discharge an inductor, and again, what I mean is after an infinite amount of time, switch S1 here has allowed current to flow for a long, long time, right? We're up to a maximum current in the circuit. We disconnect S1 and we just allow S2 to be connected to B there, such that current now just flows in R and L. So just that right half. The direction of which will be in the opposite direction that current flowed when it came from the battery. Right? That's because, again, there's an induced current from the inductor, induced that direction. So let's see how we write that in terms of Kirchhoff. So we have just now R and L, so basically 0 is L di dt plus IR, right? There's not necessarily a voltage source, but there's still a current, right? There's a residual current, if you will. So again, this is a differential equation, a little bit simpler than the last video. So the solution, a little simpler. I of t is that same I max. Now it's just times e to the negative t over tau. And it's the same time constant, by the way. So tau is L over R. Okay. All right, so let's take a look at some limiting cases. When t is 0, right, when it's fully charged, when that switch is just disconnected. In this case, if we put in 0 there, we get, well, e to the negative 0 is 1, so we get I max. Which should make sense, right? It's kind of the backwards way from the last video. When t is an infinite value, plug in infinity there. E to the negative infinity is 1 over e to the infinity, which is basically 0. Right? So it's pretty much the opposite of charging, which, again, hopefully should make sense. Let's graph this as a function of time. So now it starts at t0 with some maximum value, I max. And again, I max is equal to epsilon over r, and that's dependent upon the circuit elements. So if it starts there and it's an exponential function, looks something like this, right? It decreases quicker earlier, and it kind of tapers off, right? So it asymptotically approaches 0 over time. After one time constant, right there, the amount of current should be roughly the difference from one time constant when it was charging. In other words, it should be about 37% of I max, right, after one time constant. After 2, it should be about 14, I believe I have, right? So after t is L over R, the current, we'll write it like this, is equal to 0.37% of I max. After 2, it should be roughly 14%. Okay. And again, this goes back to the nature of a time constant. For RC circuits, the time constant tau was RC. For RL circuits, tau is L over R. Okay. And what this graph shows you is that, well, very quickly, what happens to the current? It drops off very quickly, right? So once you disconnect, the inductor does not do a great job inhibiting the change or the flow of current. Okay, And then it takes a very long time to inhibit the rest of it back down to 0, right? And if we were to charge it back up again, so reconnect S1, it'll look just like earlier, like that. So again, after one time constant from now this position, it should be back up to, not drawn to scale, should be back up to 63%. Okay. But this is the shape for an exponential, right? And this is what happens to the current in an RL circuit for a charging and a discharging inductor.